Today we're going to try to do sections 3 and 4. And then that means next Tuesday we'll finish up the course. We'll do 5 and all of chapter 6. So let's start with chapter 5, section 3, logarithms. Okay, last time we talked about exponential functions. And those look like this. Where this is our base, and that's our exponent. The graph of this function this is if a is greater than 1. And it always crosses through 1. Then we also had another graph that looks like this. That's if a was between 0 and 1. Now, the inverse of exponentials is a logarithmic function. In a logarithmic function, we write like this. It's read the log base a of x is y. The log base a of x is y. And I'm going to go ahead and show the conversion of the two. Exponentials and log. This is 5.3. Yeah, we finished 5.1, 5.2 last time. So let's say we began with this equation. Log base a of x is equal to y. The conversion, we should be able to go both ways. Because remember, this is the base. That's the base. So the a has to remain the base. So it comes over here and is the base of y. So we have ay. Since the base is gone, the log drops off, and we end up with x on the other side. So that's the conversion. So the a picks up the y and the log drops off. Then all we have is a to the power x. Conversely, we go back and forth. So let's look at the graphs again of those. Examples 1 and 2 are the graphs again. This is a to the power x. This is also a to the power x, but a is between 0 and 1. A is greater than 1. Right, so let's look at some, that was just example 1. Let's look at example 2. It says find each of the following. So we have log base 10 of 10,000 equals y, some number y. What a logarithm really means is this. What it means is this. What power y should the base get, the base is a, to equal 10,000 in this case. That's what a logarithm means, is what power should 10 be raised to equal 10,000, which is when we convert these, we get 10 to the power y equals 10,000. So the base is still the base. According to the base property, of equality, a to the power n equals b to the power n. The only way they could be equal is if the bases are equal. Then the power property of equality says if I have the same bases, because the base property says as long as the exponents are the same, the only way they can be equal is if the bases are the same. The power says if the bases are the same, then the exponents must be the same. So same bases means the same exponents. The same exponents mean the same bases. So what does that mean to our example? Whenever you're faced with something like this, well, let's work it out. We have 10 to the y. What is 10,000 written as? It's actually 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. So it's 10 to the fourth. Easy way to do this. Since you have a number like this with a 1 in front, just count the number of zeros, and that tells you the exponent. Since we have the same bases, y equals 4. So the answer to this equation, log of base 10 of 10,000, is equal to 4. Log base 10 of 0.001. So we know it has to equal something. So I'm going to say it equals y. Let's convert it. So we have 10 to the power y is equal to 0.001. Since there's a 1 here, that means it's a base 10. It just moves 1, 2, 3. So 10 to the power -3. Since we have the same bases, that means y is equal to -3. This answer is -3. Log base 2 of 8 is equal to some number y. Yeah, to solve this, the base pushes up the solution equals 8. Well, let's see what 8 is made up of. 2 times 4, 2 times 2. So 8 is made up of 2 times 2 times 2, which is 2 cubed. Since the bases are the same, y is equal to +3. The next two of this sequence are actually properties. Log base 8 of 1. We convert this, so it's 8 to the power of y is equal to 1. The only way that could be possible is if y is equal to 0. Anything to the power 0 is equal to 1. So y is equal to 0, which is a property. Log of anything if of 1 is always going to be 0. Because the graph of a logarithmic equation looks like this. When x is 1, y is 0. And the last of this example, log base 8 of 8 is equal to y. Yeah, so this is a property. Eight to the power y is equal to 8. Eight is the same thing. It has a power of 1. Since the bases are the same, y equals 1. So the rule here if the base and the number are the same, then it equals 1. So that's how you solve if I give you a logarithmic equation. Remember, the conversion we use that formula for the conversion. Example 3 asks us to convert. So the first one, it has 16 equals to 2x. We'll convert that to logarithmic equations. So we're on this side. We have to put it in logarithmic. So we have log the base. Since that's the base of the exponent, it's the base of the logarithm. This is x and that's y. Remember when you do inverses, you have to switch x and y. So this x goes in place of the answer and the y becomes that part. So you see the answer, the equals answer goes inside the function. The exponent is the answer. Ten to the negative 3 equals 0.001. Convert that to a logarithm. What's the base? 10. Very good. Since this is the equal part, it goes inside the equation. And this negative 3 goes over here. Because now if we go the other direction, 10 to the power negative 3 equals that. But how would you write that answer? If you had to put it in there, we have one shot at getting a right answer. How would you enter that answer in the computer? What is log base 10? It's a common log. Remember, if there's no base there, it's automatically base 10. E to the t equals 70. So the log base E of 70 equals t. But we're not done. What is log base E? The natural log. This is what you would enter. Remember last class, we talked about the 3 different types of logarithms, depending on their bases. If it's log base 10, it's just log of x. If it's log base E, then it's ln. Anything other than 10 and E, you have to write down those numbers. So that's going from exponential to logarithmic. Let's reverse the process. Let's go from logarithmic to exponentials. Yeah. Example 4. I give you log base 2 of 32 equals 5. Convert that to exponential. This is, again, going from log to exponential is pretty easy. Just move the base under the answer. So it's 2 to the 5, and the log drops off. And there's your answer. Log base A of Q is equal to 8. Yeah, the base pushes up the answer. The log drops off and left with Q. X equals log base T of M. The base is T, so it pushes up the answer. The log drops off, and we get M. These next two are not in the examples, but I really think they should be. ln, what is ln? Log base E, very good. Now we go ahead and do the conversion. E to the power X equals 3, and there's your transformation. And log 9, what's the base here? If it's not there, it's what? Very, very good. It's a common log, right? Log base 10 of 9 equals 2x. So the base pushes up the exponent, the answer. So far, so good. And again, if you ever get stuck, always write down the the conversion process. A pushes up the y and equals x. Again, it's an inverses of each other. X and y here, since this is the answer, they have to switch places. Now the x becomes the answer. So that's your formula. Finding logs on a calculator. But sometimes you're going to have equations that are not just straightforward like we just did. So in this one, let me write down what these are. This is log of 6, 4, 5, 7, 7, 8. Log of 0.0000239 and log of -3. All right, so if you don't have a calculator or the one on your phone, you could just go down here and type in calculator, and it'll give you an app that's already a calculator. And if you go up here, you can change the type of calculator you have. You can go to a standard basic one that has really nothing. Or we can use here the scientific. Actually, if you want to, also when you're doing your work, you can use the graphing calculator. And if you notice here, there's log, there's ln. Let's see, let's look at log of x. Log of x. I put x and log of so log of x is equal to that. Again, it's got a vertical asymptote. It never touches the y-axis. It goes on to -infinity. It crosses always at 1, and it goes to positive infinity on the domain. Notice these also have trigonometric and inequalities. This will help you if you get stuck doing inequalities. So the way you do these is just type in the number first. I believe in these is just type in the number first. And then take the log of it. And there's the answer. And what does that number represent? Remember, for logarithms, this is base what already? Base 10. So if I take 10 to the power 5.8100832, whatever, I'll equal this. This is the exponent to the base. Now, we don't want to have a million decimal places. So for this example, let's always round down to 2 decimal places. Remember the rounding rules? Here are the rounding rules. So if rounding to the second decimal place, go to the third decimal, and do the following. So since in our example, since we're rounding up to 2 decimal places, we go to the third decimal, which is 0. If the third decimal in this example is between 0 and 4, then drop all numbers after the second decimal. Since we're rounding it to 2 decimal places, we look at the third. It's 0, so I just get rid of those. So my answer is 5.81. If it if the third digit is between 5 and 9, then add 1 to the second decimal and drop all other numbers. So if since we're rounding it to 2 decimal places, look at the third decimal. If it's between 5 and 9, just add 1 more to the second decimal and drop everything else. All right, so let's look at log base 10 of 0.00000239. So I come back over here, multiply by 0 to clear it out. So I have 0.0000239, and I take the log of it. Since it's a very small number, 621602099. Okay, for this one, let's round to the third decimal place. So since we're rounding to the third place, we look at the fourth number. It's greater than 5. So I drop all of these and add 1 to that one. So it's negative 4.622. So far, so good. So that's for logarithms using the decimal places and rounding. How about the third one? What do you think this is going to be? Log base 10 of negative 3.
Positive.
No. Remember the graph? The graph of logarithms looked like this, right? Can you use a negative x? No. So this one does not exist. Or your calculator will simply say error. To a calculator, this is the same thing as saying divide by 0. Not going to happen. So this is example 5. Okay, example 6 is going to look at natural logs. Example 6. Okay, so this one we have ln of 6, 4, 5, 7, 7, 8. ln of 0, 0, 0, 0, 2, 3, 9. ln of -3. ln of e. And ln of 1. Again, so with these, let's go back to our calculator. Let's do the first one. Clear this out. So I have 6, 4, 5, 7, 7, 8. I go to ln, I take the ln of it. Equals 13.378, 2110, and so on and so forth. But you see now why we deal with rounding, because you don't want to write all of these. This is more accurate, but because this makes it easier, if we round it to 2 decimal places, what do we get? Very good. So if we round it 2 decimal places, we look at this one, it's 8, so we add 1. So it's 13.38 and drop everything else behind it. These are on the sheets I gave you last time, so you don't have to hurry up and write this stuff down. It's on the sheets I gave you last time. Okay, the next one is 0.0000239. I take the ln of it. -10.641632, and so on and so forth. Same thing again, rounded to 2 decimal places. We look at the third decimal, it's a 1, so we just drop them. So we look at the third decimal place, it's a 1, so just drop them, and we have 2 decimal places. C, the third one, ln of -3. So if we do ln of -3, we do a -3 and take the ln of it. What do you think is going to happen? Error. The reason is you cannot, again, this is a log base E. The graph of logs all look the same. You cannot have negatives. So this does not exist. Or error. The last two we've already done. I've set out those rules already. What's this one going to equal? Very good. It's going to equal 1 because ln is log base E of E. Since these are the same, it equals 1. And this one? Very good. Log base e of 1. Anything log of 1 is always 0. Those are properties. Okay, notice on this calculator, and all calculators thereabouts, you notice you only have log and ln. We don't have log base 5 or log base 3 or log base anything else. Calculators only have log base 10 and log base e. So they have the common log and the natural log. So if you have any other log, with bases other than 10 or e, then we must use the change of base formula. Basically, what this says is we have to change an equation that looks like this into only having either log base 10 or log base e. The change of base formula is this. We can either use the log base 10, the common log, or we can use the natural log. Because it's the ratio that we're looking for. So if we had something like this, we couldn't use a calculator for it. Whatever's on top, the operation that goes on top, whatever the base is, stays on the bottom. If I want to use the logs, I'd use this. If I want to use the natural logs, I'd use this. The ratio is still going to give you the same answer. So let's look at example 7-8. Log base 3 of 8. It says use common log. An example 8. Use natural log. So what would example 7 be? What's the answer there? Gotta be a fraction. Common log is base 10. So it's log. The top number goes on top. And the bottom number goes on the bottom. There you have it. You just type it in the calculator, log 8 divide by log 3, and hit enter and give you the answer. The natural log is ln. So it's ln of 8, ln of 3, and those are your answers. Now I want to look at graphs. This is going back to what we did in section or chapter 2, section 5, transformations. Example 9. The log base a of x remember, logs cannot, you have negative x's. Can't you take the logs of the negative numbers? It always crosses through 1. Looks like that. The only difference is if it's a log base, whatever, it changes amplitude. And you have to find some points there using calculator. Same thing with example 10. The function is ln of x. Crosses through 1. Has a vertical asymptote at the y equals 0 or x equals 0. Let's graph these functions. Ln x plus 3. What's going to happen to this graph? Which one? Well, how do we do it in chapter 2 in transformations? Whatever if it's inside the parentheses, take whatever that is, set it equal to 0. It's a horizontal shift 3 to the left. So our original graph looks like this. This is ln of x. But our graph, the origin, moves back 3 spaces. So we have our new origin here. So it crosses at 1. So everything just moves back 3 spaces. So the whole graph picks up and moves back 3 spaces. My origin used to be at 0, 0. Now it's at -3, 0. That's a horizontal shift. Let's look at B. F of x equals 3 minus 1/2 ln x. So the original function is ln x. The graph of that one looks like that. There's no horizontal shift because it's just x. There's no x plus or minus anything. So what happens to the 1/2? It's outside, so it's a vertical shift. What it does, it's a vertical shrink. It pushes it down. Instead of this being 1, it's now going to be 1/2. Now working way out, we have a negative here. We have a negative 1/2. What that means is no matter what this becomes, this is my y answer, but now it becomes negative. So that means I flip this. My positive answers become negative, my negative answers become positive. So I flip it and it becomes like this. It flips across the x-axis. And then we have a positive 3 in front of that. Since the 3 is not related to x in any way, shape, matter, or form, this is a vertical shift. It's positive, so we go up 3 spaces. This is our original x-axis. The graph originally went like this. So now my origin goes up 1, 2, 3 spaces. So now my origin is shifted to this one. So the whole graph moves up. So instead of crossing at 1, 0, it now crosses at 1, 3. Again, it's the same thing we did in chapter 2 for transformations. The absolute value of ln x minus 1. So the original function is ln x. It looks like this. Crosses through 1. But then we have an x minus 1 here. What does that do to it? Very good. Shifts it to the right 1 space. So I move the origin 1 space to the right. That means my graph, the asymptote is 1, and it crosses at 2 now. Because I move everything over one space. Now comes the interesting part. Now I put the absolute values around it. What does the absolute value do? What does absolute value do in general? Makes it positive. So I cannot have any negative answers. That means my graph it has a point at 2, and the positive ones stay positive. It's just now these negative ones have to, this part here has to flip across the x-axis. Instead of being negative wise, they have to become positive wise. So it still touches that 2, but instead of being negative, I rotate it up. And it has to get close to the vertical asymptote. And example 13 is simply an application, and that's why I went ahead and did the whole thing. The formula you use for concentric circles of a shock wave earthquake is actually, this is the for tsunami, when the original shock wave, log base 10 of I over IO. And then look them here, see what they're giving you. The IO is the minimum intensity level. And what is its intensity here? Measured Richter scales are, find the intensity of I, and I sub O is the minimum. So in this case, we're looking at, had an intensity of 10 to the 9th times 1, 0. So our equation, the Richter scale, becomes log base 10. Our I is this. 10 to the 9th times I sub 0 over I sub 0. So those cancel. So it's log base 10 of 10 to the 9th. Log base 10 and that one cancel. So the Richter is 9.0. Oops. Let's look at the properties of logs. And back on the last sheet of your assignment sheet, it's just practice graphs again. Hopefully you get to a point where you can just look at those and see what functions are which graphs. Yeah, I'm gonna stop this video and start it again for the next section.